Can you hear me?
Yes.
Yes. Okay. So what I'm going to present is following some of the talks we heard by Rodrigo and Mark Buey. It's a case for an automated occultation network with a slightly different purpose than some of what we've heard. This is very preliminary, just an idea we've been working on, thinking if it's useful for anything. And we'll see some of the preliminary results. So what are we speaking of? Order of 100 telescopes, really nearby each other, like 1 to 2 kilometer spacing, with fixed location, all automated. We'll be searching for precise astrometry from predicted occultations of Gaia stars by main belt asteroids. So we're looking at the inner solar system for these occultations. Why look at the inner solar system, and what does this have to do with TNOs and the transneptunian solar system? If we look at around 1 million MBAs of like 1 kilometer or larger, the known population of MBAs, and we have really good orbital constraints for them, really good astrometry. This can eventually be looked as a test case for tidal fields of the outer solar system. We're not thinking of like dynamical effects that would have evolved over the millions of years, but the actual tracking during, for example, a 10 million period, a 10-year period. And if we're able to get sensitivity to some gravitational effect of the outer solar system with this kind of tracking, this idea was roughly inspired by this Malinorais paper from 2019 that discusses constraints on tidal fields from planet X, also from a different set of occultation telescopes. So survey design is just, we need somewhere with a straight line north-south in the middle of the desert. It could be Chile, it could be Nevada, somewhere in the US, even Brazil, like northeast Brazil. We'll have a number of telescopes, which we'll call N. We still don't know what's the optimal amount, still don't know the size. Both the size of the telescopes and the amount of telescopes will drive the cost. So these two parameters depends on what we want the cost of the survey to be. About our target population, here's just some scalings and interesting stuff to choose. So when you're thinking of the diameter of the target objects and the heliocentric distance, we have this diffraction limit that's about the point when this diffraction starts affecting our results. The depth of the occultation starts narrowing, so we lose precision. There's a point here, this is not a rough limit, just to show that this happens when we go up with the size. We also lose a little bit of the depth of the occultation because the asteroid starts being bright as the star, so we won't get a really good depth. You also have the limit of discoverability by OSST. And here we see that this really small number of asteroids, a million of them, for example, are there in the JPL database, fall in a good region, and we have having a good amount of orbits can kind of drive the uncertainty down. So I want to talk about what would be the sources of error involved for this precise astrometry of these objects. One thing we need to think is the shape noise. So basically, what we are interested in, if we want to track the orbits, is the center of mass of the asteroid. And if you have like really small asteroids, 1 kilometer, 2 kilometer size, even if the telescopes are at this distance, you get 1 or 2 chords. You won't get enough chords to be able to say something about the shape of the asteroid. So the shape will basically appear as a noise. You have these chords. If you have 1 chord, your best guess is the middle of the chord. With 2 chords, you can try different methods to guess the geometrical center, which is also not necessarily the actual physical center of mass because we're not taking density models into account. So all this would come in as noise in our astrometry of the center of mass. And we use some shape models of asteroids to try to determine what would be the fraction of the asteroid size that would suffer from this effect. And this is around 10%. But again, this depends on like shape distribution of these asteroids that we also don't know much about. So this number is still just an estimate. Some other sources of error, as I said, diffraction decreases the occultation depth, and this will affect our power of actually constraining the ingress and egress time of the occultation, which is what I called here the timing accuracy. In the end, timing is not necessarily timing of the clocks. When I talk about timing accuracy, I mean at what point in the curve you can actually distinguish the depth from just randomizing the photon counts and to actually determine like the position of the beginning and the end of the chord. So diffraction affects this because occultation depth the occultation becomes shallower, and it's harder to get this. You have the stellar astrometric errors, stellar angular diameters, and the shape noise, which I already mentioned. We also have some additional things that are not taken into account in this model, and we're still working on taking into account. For example, noise from eventual encounters that disrupt one orbit or the other. If we don't know about these encounters, this would also be some kind of noise that appears on the orbit. So now, having looked about our targets and our errors, we'll talk a little bit about how we simulated this survey to try to get any results. So we generate random events based on the actual MBA orbits and the Gaia star density at the point. So there's no need at this point where we're just investigating if this is something interesting to do. There's no need to actually predict the events. We won't even be able to do it because we don't even know where the telescope would be. But we can get good statistics on the amount of events and what can we get of them. If we basically get these orbits and see where they're passing in the sky, what's the star density for each magnitude, for different magnitude limits, and use this to generate random events. And here we also have some assumptions. One of them is that all the orbits are known well enough to catch an initial occultation. So we heard from Mark's talk, for example, that it's hard to get the first initial occultation and still don't have good astrometry on the object. And here this kind of as an assumption that with the 100, 200 kilometer size array, we'll be able to catch the initial occultation. We're also not considering problems with simultaneous occultations. So we're assuming that this will get a huge amount of occultations, but after the first occultation, you can restrict more your predictions, and you can have different telescopes looking at different occultations. You can, for example, predict that one occultation will happen between telescope 50 and 60, and only these 10 telescopes are looking for this occultation, and the other parts of the array are looking at different occultations. So we assume that this would kind of solve the simultaneous occultations problem, which seems reasonable with the numbers we have for now, but may have to be revised. Now, finally, in terms of the goal of the project, what we want to get with this, sensitivity to gravitational perturbations. So the observable effect of a distant point mass would be basically a tidal field. If you expand its gravitational potential, what you can actually see, and the strongest signal would be a tidal field. It's a function of the mass and the distance from the sun to the third power. So this means that we're not separating mass from radius of any object we're trying to fit. So suppose this happens, we get this really good astrometry in the orbits, and we're able to fit a model with a distant point source. You can say 5 Earth masses at 800 astronomical units would have kind of the same effect as a Mars-sized habitable planet at 220 AU. Then you would need other methods to try to distinguish between these scenarios. So you're detecting the tidal field and not the actual mass and distance separately. So finally, how do we predict the uncertainties? We use a Fisher matrix formulas. So we need a model, solar system first. We use the 8 planets with 6 state vector components and their mass, plus the large MBA masses, hyperbolic rings, actually 2 rings with, you can leave the radius as flexible to try to model the things in between them. And use 5 extra point sources at 400 AU as our possible point masses. The reason we use 5 of them is because you can use linear combination of the tidal field generated by each of these 5 points to try to predict what would happen if your point was anywhere else in the sky. So then we run n-body simulations with rebound and get derivatives of the observables with respect to all these parameters. We add the predicted occultations, which we has to be at least 5 per MBA, because you need at least enough to constrain the orbit and see if it's different than an actual orbit. And prior some of the masses obtained by other methods. We add all this to the Fisher matrix, marginalize, get a 5 by 5 covariance matrix for the 5 tidal field components based on the derivatives with respect to these 5 masses. And this gives us a way to predict the lower bound of the uncertainty of a mass scaled by radius for a point at any angular position in the sky. So here are some preliminary results. This plot here shows different possible arrays. Here would be the number of telescopes and here the telescope diameter. So the colors here would be our sensitivity to this point mass. And this is basically for a point scale, for a point source at 400 AU. So this white line, for example, this is 0.125 Earth masses SR sigma if it's scaled at 400 astronomical units, which would be equivalent to a 5 sigma detection of that 5 Earth mass 800 AU or Mars size 200 AU planet that I showed in the previous slide, that it would have the same effect. Then we use a simple cost model here. Here we assume the cost is proportional to the area, which seems kind of reasonable for telescopes on this range by our research. So this is just a simple estimate of the cost per station, which includes a term for proportional to this area, and then another additional term that doesn't depend on the area, which would be the rest of the equipment needed for each station. This is just, obviously there would be more costs, even legal costs for the land and other kind of stuff, but this is just to see a little bit of the scalability and to try to optimize the array in terms of this result. What we want is the best sensitivity possible. How can we optimize the array design given a specific budget? So what we see, for example, if we want a 5 sigma detection of that hypothetical case that I showed, whether it's a planet 9 or Kuiper planet, you can see these lines touch here approximately in this region, so we'll be talking about $10 million budget around this region. The optimal would be around 4 centimeters with 150 telescopes. Here, these plots show a little bit in more detail this prediction. So in the previous plot, I was talking only about the upper limits, like what's the sensitivity that we would get for anywhere in the sky. Like any position in the sky, we have that sensitivity. And now this is the cumulative fraction of the sky, because depending on where on the sky the planet would be, we would have different sensitivities. So current data is what we can actually do with Juno, Cassini, Mars data, actual data on the position of the solar system. This is what we have been using for the orbital fits of the solar system and testing planet models. And we see this extremely optimistic improvement. It seems extremely optimistic for 3 scenarios of 50 centimeter 50 telescopes, 150 40 centimeter telescopes, and 340 centimeter telescopes. And this line would be like the threshold for that scenario. Sadly, this is not exactly true, because we have uncertainty in the tidal field of the Kuiper belt itself. So basically, you have a fundamental degeneracy when you're trying to look at something further away from the Kuiper belt. We can't say if the signal is actually coming from one source outside, or if it's the uncertainty on the mass of a large ABO or quadrupoles from the Kuiper belt. This uncertainty we estimate to be around here, which kind of drags all the curves back. But still, we see that same preliminary result that the 150 40 centimeters telescope would be able to find this hypothetical planet anywhere in the sky. So moving forward, some conclusions. First of all, we have done a similar work, which is in this QR code, assessing the usability of the LSST data on the Jovian Trojans as test particles for this distant mass. You see that these observations would be way more useful than this. This is mainly because of, with the occultations, you can get good astrometry of really small objects, which would not be possible just with the actual looking at the objects, even with the LSST. We see what we could get with the order of 10 million array. And further use, if such a network existed, we could use it not only for this purpose, but we could also use to get shape data on TNOs, 10 to 100 kilometers high TNOs. If we have a TNO occultation passing through the array, we will get really precise shape data. Measuring asteroid masses from mutual deflections of the main asteroids we are tracking, and even people who are interested in modifying gravity or testing also gravitation could also use this, could also appreciate this precise astrometry. in something that's not on the slide, but this could also be used for a first occultation. One of our previous idea, you can track the first occultation with our array, and then we have the second and third with this set of telescopes. So this is it. Happy to answer any questions.
And we have time for one question or two.
The uncertainty that you said about the Kuiper belt will improve with LSST, knowing if you multiply the number of known objects by 10, will that improve or it still will be that bad? That uncertainty.
This would not necessarily help because this thing here is driven now by the uncertainty on the mass of large TNOs. So not necessarily not knowing enough TNOs, but being able to constrain in a way that's independent of solar system like orbits, like moons or this kind of stuff, being able to constrain the mass of the large hyperbolic objects, but definitely knowing their distribution or the general distribution, Kuiper belt design of where things are would definitely help a little bit. But yeah, this is dominated by uncertainty on the mass of large TNOs.
Yeah, just a quick question. I was curious, since this is a set of automated telescopes, and Rodrigo was talking about a set of automated telescopes, are there ways that those things could be done simultaneously with the same?
Kind of, we have to think about, but the main difference is that here I think the telescopes that are really close, if we want like small mean-belt asteroids, that will just slip in between if there's a 20 kilometer distance or anything, but we can think of ways of trying to use something for the double purpose.
Thank you for the talk. This is super cool. Would this experiment constrain the Kuiper belt tidal field as well?
Yes, the fact that these slides show that without uncertainty this would be getting here, and our current knowledge of the Kuiper belt would be around here. This means that fits of the solar system using data from the sampling survey would maybe even be able to say something about this large KBO masses or something else.
Okay, you have to move to the next slide. Thanks.